Hey everybody, Mr. Smith here, and in this video lesson we're going to talk about Newton's law of gravitation, so it should be pretty fun. Let's get started. So to get a bit warmed up and review some of the things we did with uniform circular motion, let's consider the applying uniform circular motion to the Earth revolving around the sun. So what is providing, because I think we would all agree that the Earth is revolving around the sun. I think we all have an understanding that the motion around the sun isn't perfectly circular, but it is pretty close. So if it is orbiting the sun in roughly uniform circular motion, what's providing the centripetal force and how can we quantify it? Well, we actually have the tools right now to find out the magnitude of that force. And hopefully you guys all said, what's providing the centripetal force? Well, it's gravity. The sun is exerting a force on the Earth, and there is a reaction force. The Earth is exerting a force on the sun. But of course, the sun is so massive that the effects of that force are very, very, very negligible. And we see the Earth revolving around the sun. So usually to find a centripetal force, we need the tangential speed, the period, or the frequency. And luckily, we do know the period. We do know that the Earth revolves around the sun in roughly 1 year, so 365 days. And if we know the kind of radius of this orbit, which we do, it's about 1.49 times 10 to the 11 meters. And we do roughly know the mass of the sun. It's about 5.98 times 10 to the 24 kilograms. We can do this. So I thought it'd be interesting to just actually find out the Earth's tangential speed as it's flying around the sun. That's pretty cool. And then we'll find that centripetal force the sun exerting on the Earth, which turns out to be the gravitational force. And then we'll also check out use our own mass, and you can use mine if you'd like, and we'll find the force the sun is exerting on you. So I've got a slide here just to actually do some of this. So yeah, let's dive in. If you actually just if you want to just pause the video and see if you can figure out these things on your own, that'd be totally fine. So we got the period, and that's 365 days. But we would like to be working in standard units, so we're going to have to get that to seconds. So we'll take 365 days, 24 hours in a day, 60 minutes each hour, 60 seconds each minute, times 3,600. And so I'll just keep all my digits here. There are approximately 31,536,000 seconds in a year. Kind of seems a little bit depressing when you think about it that way. Count to 32 million roughly, and a year is done. But we can find the tangential speed, right? Because the tangential speed would be the distance the Earth travels, the circumference of its orbit, 2 pi r, divided by the time it takes, which is the period. And we know those things now. The Earth is about 1.49 times 10 to the 11 meters away. Period, we just got 31,536,000. And let's see what that tangential speed is. The answer may shock you. Or maybe it won't. Where's my pi button? I use it every day. And first time every day, I need my pi button. Always got to search for it. It's like plugging into USB. There's only 2 ways that you can plug a USB cord in, but it always takes you 3 times to kind of plug it in, right? So approximately 29,700 meters per second, or like basically 30 kilometers per second is what we're zooming around the sun. which is pretty cool if you think about it. That's pretty fast. All right, for number 2, let's calculate the force that the sun is exerting on the Earth. So we're going to use and the only force really we're considering here is the force of the sun on the Earth. We understand that all the other bodies in our solar system are exerting a force too, but yeah, I think we can neglect them all in this case. So force equals mass times acceleration, and the object that's moving here is the Earth around the sun. So I might just use me just to indicate, hey, we're doing the mass of the Earth. And so remember, acceleration was v squared over r. So the Fc equals ma, we get me times, and now we use v squared over r. And we actually have those things. Actually, we do need to look up the mass of the Earth, which is, we do have the mass of the Earth listed in the question. I might have said that was the mass of the sun originally. The mass of the Earth, 5.98 times 10 to the 24 kilograms. So we just found out the tangential speed. I'll just use that rounded value, not crazy big deal, squared, divided by that orbital radius. Let's see what we get. 5.98 power of 24 times 29,700 squared divided by 1.49 power of 11. So we get a pretty big force here, about 3.54 times 10 to the 22 newtons. That's a massive force. Now, if you want to, for part 3, you can use your own mass if you want, but you can use my mass if you want to. And so in part 2, here we use the tangential speed we calculated. But why don't we just to play around and do something a different way? So let's not look at the Earth. Let's look at maybe me. And let's see. We know that I'm orbiting the sun in a period of 365 days. So let's find the force of the sun on me. So I use my mass, and I'll use the period this time just as a bit of practice. So remember the equation we had for centripetal force that involves the period was 4 pi squared mr over t squared. And here we'll just see, we could have used this for part 2, but since we had the speed, I thought we could use that. But let's just use a different method for this one. So 4 pi squared, I'm around 80 kilograms, and I am the same distance away from the sun, about 1.49 times 10 to the 11. And I'm orbiting the sun once every this many seconds. So, I mean, hopefully this isn't too big because, I can be honest right now. I can kind of feel my weight sitting in my chair right now, but I'm not necessarily feeling anything from the pull of the sun, per se. So I guess it should be pretty low. And I forgot to square the bottom. Yeah, I got a value of like several million newtons. And I'm pretty sure if I was experiencing a force from the sun of several million newtons, I don't think I'd be talking to you right now. I'd be some kind of like soupy mess on the floor. Divided by 536,000 squared. That's better. So yeah, I mean, it's pretty small, 0.47 newtons. Not noticeable. So that's pretty cool, tying what we learned about centripetal force to gravity. So we've actually quantified the gravitational force between, say, the Earth and the sun in terms of uniform circular motion. But it'd be nice if there is a way to calculate that gravitational force a little bit easier, maybe not necessarily knowing, the tangential speed or period of rotation. And this is for an orbiting body. What about two objects just kind of sitting side by side and not kind of orbiting each other. So this brings us to Newton's law of gravitation. So in his Principia, or Principia, I don't actually know, published in, I think it's Principia actually, I don't know for sure though, published in before 1700, Newton described how he used known data about objects in the solar system, and notably the moon's orbit around the Earth, because that was pretty easy to collect data for. And he discovered the factors that affect the force of gravity throughout the universe. And he summarized this in his law of universal gravitation. So he discovered the following proportionalities. Okay, so I'm going to write these in terms of math. So this gravitational force between two objects, I'm going to call Fg. It was proportional to the first mass, meaning that what that means is if you double one of the masses, you double the force of gravity. But it was also proportional to the other mass too. Like if you double the other mass, you double the force of gravity. So say you double both of them, then you'd have 4 times the force of gravity. So since it's proportional to both, it's proportional to the product of the two masses, so M1 and M2. And he also found out that the gravitational force was inversely proportional to the distance between the two objects, like the center-to-center separation, but actually not just that. He found like if you doubled the distance between two objects, you don't have the force of gravity. It actually goes down by 1/4. So it was inversely proportional to the square of the center-to-center separation. So I just want to actually clarify a couple things right now, and then I'll probably make note of them later too. So this gravitational force was proportional to M1 times M2, and just to be clear, that's if R is fixed. So if you don't change the radius and just like say double a mass, it doubles the gravitational force. And for the second one, this obviously if this holds only if M1 and M2 are fixed. But this R, just to be, I might have this in the PowerPoint somewhere else. I don't know why I wrote that word first. That R is what we say it's the center-to-center separation. Between the two bodies. So got that down there. So just in case I don't have it later on, I don't forget. So we can put this into an equation. So if you combine these results, you get the following. You get that the force of gravity is proportional to M1 times M2 divided by the square of the distance between them. And being proportional means this. It means that an equation governing the gravitational force between two objects is some constant times M1, M2 over R squared. And by performing experiment after experiment, they can refine and refine and refine and find what this constant is. And this constant we call Newton's gravitational constant, and it's G. And this G, it's listed in the resources in these constants somewhere, but you'd probably just have this memorized after using it so much. It's really small. It's 6.67 times 10 to the negative 11. And the units, which you guys don't really need to concern yourself with too much and memorize, but to make all the units match up, it's Newton meters squared per kilogram squared. So this is Newton's gravitational constant. And as I mentioned before, this R is the center-to-center separation. So if you know the two objects' masses and how far apart they are, then you can calculate the gravitational force between them. Pretty cool. So I think 4 important points. So the force is felt by both objects. So it's like an action-reaction force. The sun exerts a force on the Earth. The Earth exerts a gravitational force on the sun. The same thing is happening everywhere. Like right now, as my coffee mug sits on my desk, the Earth is pulling down on my coffee mug, and the reaction force is that my coffee mug is actually pulling up on the Earth. However, the one is significantly more noticeable than the other. So the force is felt by both objects. For the force to be noticeable, one of the masses must be very large. So if you and your friend are, sitting side by side on the couch playing video games or watching a movie, you don't need to worry about the two of you coming together and smashing together because of gravity. One of the masses must be very large, like a planet. This force diminishes quickly for increased values of R. So for those of you who have taken some functions courses, the graph of 1 over x squared gets really small really fast because when as x gets really big, when you square a really big number, you get a really, really, really big number. And then 1 divided by a really, really, really big number is very close to 0. So this force really diminishes quickly as R gets big. And finally, gravity exists everywhere, but may be negligible due to its weakness. So you don't have to, we were doing our 2D dynamics problems last unit, like we didn't need to factor in the force of gravity from the sun and the moon and that star several million light years across the galaxy. No, we just neglect those because they're not. It's not that they don't exist. It's just it's so weak. Well, I have a fifth one. The law applies to objects that are spheres, and their sizes are much smaller than their separation. You can copy this down or not, but the reality is, most shapes aren't spheres. Like we're not spheres, right? But if you have an object that's not spherical, and you have an object down here, well, this point, maybe that the mass in this part of the object pulls it this way, the mass of this part of the object pulls it this way, and things get kind of complicated. If you know the mass distribution, you can deal with it, but that's for like a higher level university course. So for us, we just treat things as point masses, as spheres, and with a separation of R, and they just attract each other. So we keep things simple. And the sizes are much smaller than their separation. So meaning we're not doing two big spheres that kind of like overlap with each other. Because it'd be kind of silly to think about the gravitational force between the Earth and the sun if the Earth and the sun were 1 meter apart, because that would be impossible. How can the Earth and sun have a center-to-center separation of a meter? Kind of weird. So we're assuming things are like small point mass spheres, and their sizes are much smaller than the separation, which is true. Like if you were to look back at the sun and the Earth in our solar system from far away, the distance-wise, they're very. They're very small compared to how far apart they are. So how did physicists determine this gravitational constant G? And the answer is the Cavendish experiment. So in a simplified version of this Cavendish experiment, you had two small spheres on a thin rod, and it was hung from a very thin torsion wire. And as you brought larger spheres close to these smaller ones, they would exert a gravitational force, very small. However, if the equipment was precise and delicate enough, then they would still exert a gravitational force, and by doing so, it would cause the apparatus to twist. And by kind of measuring the twist, the torsion in the wire, they're able to, see what happens when they change the masses, use different masses, use different separations, and they're able to determine G to fairly precise values. If you want, from here, you should be able to snap this QR code. But I will also post the link to that video on Brightspace if you would like to see the famous physicist Richard Feynman do in one of his lectures, just talk about the Cavendish experiment. So it's like old school cool. Check it out. Let's do a few examples, get used to this idea. We're going to find the gravitational force between the Earth and the Sun. And hopefully we get something similar to what we got earlier, but using Newton's law of gravitation. So Fg equals G times the mass 1. So I might just use sort of mass. I just might use ms for mass of the Sun times the mass of the Earth divided by r squared. And so at this point, I might just take a pause and remind you guys that for when you're doing problems today involving gravitation and satellites and Kepler's laws, you don't have to memorize these values or go to Google. The solar system data we need has been provided for you. And it is on Brightspace, under formulas and useful stuff, solar system and radioisotope data. We want the solar system data. So you can see we have the mass for these are the bodies in our solar system, and the radius of each of those objects. We're not really interested in that quite for now with this problem. Period of rotation on its axis. So this means how long it takes for the object to spin. And so if you look at the Earth's 8.64 times 10 to the 4 seconds, that's about a day. Mean radius of orbit. So this tells you, if you assume these guys are rotating in a circle around the Sun, it tells you what that average distance is. So this is the value we used earlier, 1.49 times 10 to the 11. That's on average how far the Earth is from the Sun. Notice there's no value for the Sun because it's not orbiting itself. For the last one, for the Moon, this is clearly the distance from the Earth to the Moon. The Moon is orbiting the Earth. In the second to last column, you have the time it takes to revolve around the Earth. Or, excuse me, the Moon would be around the Earth, but this period of revolution is the time it takes these bodies to orbit whatever it's orbiting. So for the planets, it's the Sun. So for our question, right now, we need the mass of the Sun. So 1.99 times 10 to the 30. I think the rest we've used. So 6.67 times 10 to the negative 11. Mass of the Sun, 1.9 times 10 to the 30. Mass of the Earth, 5.98 times 10 to the 24. And the distance between the Earth and the Sun. So this is the center-to-center separation. Why we say that is, you never need to think, oh, do I need to subtract the radius of the Earth and the radius of the Sun? And you don't, because those two things are so small compared to how far apart they are. We're not going to consider it. So how far apart they are. And we have it earlier. You guys probably have it in front of you, but instead of flipping to my solar system data, just consult. I did this problem earlier. So I have 1.49 times 10 to the 11, and don't forget to square. So Newton's law of gravitation, pretty easy to set up. You've got some big numbers and some small numbers, so you might have to brush up on how to do scientific notation on your calculator. But overall, it's pretty friendly formula to use, pretty powerful formula. X11 squared. Okay, so I got 3.41 times 10 to the 22 newtons. And that does seem familiar. If I go back to our work from earlier, 3.54 times 10 to the 22. So not too shabby. 3.41. Yeah, our work from earlier was pretty good, but this is a bit more precise value using Newton's law of gravitation. So yeah, that's cool. We got pretty close earlier just by using uniform circular motion. That's great. All right, let's continue. Let's do a second example. So let's look at what happens when we make changes to a scenario. So let's say we have two masses, M1 and M2, and they're r meters apart. What would happen if we double the masses and triple the separation? How would the gravitational force be affected? So there's lots of ways to do problems like this. Like you could just plug in numbers and just compare numerically how it works. I kind of prefer to do things in a general sense. So I'm just going to say F old. So the old gravitational force between these guys would be G M1 M2 over R squared. But now we're going to change things. So G is still G, gravitational constant. Now we're doubling mass 1, and we're doubling mass 2. So alone, that would do 4 times the force of gravity. But we're also tripling the separation. So what's going to win out here? And careful, so that's 3 times the old radius, and we're squaring that value. So it doesn't take a lot of heavy math to see. We're going to get a factor of 4 on top, and 3 squared is 9. So what we're going to get is we're going to get 4G M1 M2 over 9 times R squared. And if you look at this, G M1 M2 over R squared, that's just the old force of gravity, right? So the new value is going to be 4/9 the old value. And so you won't have as strong a force. So even though you're doubling each mass, the effect of tripling the separation has a bigger factor because Newton's law of gravitation, the gravitational force is inversely proportional to the square of the radius, while it's just proportional to like just the mass. So the squaring it wins out. It's less than the old guy, and it's exactly 4/9 the old force. That's pretty cool. What other thing can we do with Newton's law of gravitation? So one cool thing we can talk about is Lagrangian points. So this idea of Lagrangian points is pretty cool. It's the point between two objects where the gravitational force, the net gravitational force is 0. Which means one object might be pulling to the one way and the other object's pulling it another way, and they're perfectly balanced, so it actually doesn't move. So any two gravitational or any two masses will have some Lagrangian point between them. But later on, and some of you guys may study this stuff in university, if you look at so I've drawn a crappy sun there, and this isn't to scale, but we've got Mercury's orbit, Venus's orbit, Earth's orbit, Mars's orbit, and I'll leave some space in Jupiter's orbit. And some of you guys may know there is an asteroid belt between Mars and Jupiter. There is an Earth and Mars. I don't think it matters too much, but that's actually kind of it's not a Lagrangian point, but it's like a region of a Lagrangian region in 3D space where the gravitational force between what's outside this orbit and what's inside this orbit is kind of balancing out, and you accrue all these little tiny small masses, asteroids, in this orbit. So that's why we kind of have an asteroid belt. It has to do with gravity and Lagrangian points. But the math is, because it's not just points, it's actually pretty complex, way beyond the scope of what we're doing. So sorry, I digressed a lot there. Let's get back to our example. So at a certain point between two masses, the net gravitational force is 0. So let me just draw our diagram here. So we've got, say we have mass 1, and this guy is 10 kilograms. And we've got mass 2. Let's call that one mass 2, 5 kilograms. And we are going to imagine some third mass somewhere in the middle. I don't know where it is right now, so I'll just call it M3. And we don't know its mass right now. We might see later that doesn't factor in. So we want to find where this is. So I'm going to let the distance, I'm going to let x be the distance that this third mass is from M1 at the Lagrangian point. And the remaining distance, because M1 and M2 are 10 meters apart, then an expression for the distance between M3 and M2 would be 10 minus x, right? Like if x was 1, then the other distance would have to be 9, 10 minus 1 for them to add up together. And we're going to set up a little equation here. So the key is at the Lagrangian point, the gravitational force of mass 1 on mass 2 is going to equal the gravitational force of mass, I should say, I'm just going to erase that because it's 1 on 3 we're talking about here. Equals the gravitational force of 2 on 3. And I might mention too, Newton's law of gravitation here gives the magnitude of this gravitational force. So we understand that two masses will attract due to gravity. This formula here takes care of the magnitude of that force. So right here, we're setting the magnitudes equal because we know that mass 3 will be pulled towards mass 1 and towards mass 2. Mass 2 is going to attract it towards it. And we want to find that distance so that these two magnitudes will be equal and things will be perfectly balanced. I feel like I need like a image of Thanos there. So let's go on here. So what is this gravitational force? F13, it would be G, M1, M3, and the distance between these two guys we said is x squared. F23 is G, M2, M3, and that distance was 10 minus x squared. So this looks like a pretty messy equation to solve, but don't worry, it's not too bad actually, because if you think about it, we've got a factor of g on both sides that divide out, and we have a factor of m3, so it doesn't actually matter what the third mass is. This point where the gravitational forces are balanced would be true for any mass. And then let's plug in what we know. Mass 1 is 10, so 10 over x squared equals 5 over 10 minus x squared. And I bet a lot of you guys have actually solved equations like that before. You may be thinking, well, how do I do that? The variable's on the bottom. Well, if you just do a little trick and just do some cross multiplying, you get 10 times 10 minus x squared equals 5x squared. And now it looks more like a quadratic equation. And actually, if we were to be smart about this, we can divide both sides by 5 and be left with something a lot easier to solve. So yeah, now we're kind of like teleported back to grade 10 math. Let's solve this equation. So 10 minus x times 10 minus x would be 100 minus 20x plus x squared equals x squared. Expand that out. 2x squared minus 40x plus 200 equals x squared. And bring that x squared over. Subtract. So 2 minus 1 is 1x squared minus 40x plus 200 equals 0. And I don't think that can be factored, so we do need to use the quadratic formula here. I did this earlier, but I'll just do it again. So we have negative b, so 40, plus or minus the root of b squared, so negative 40 squared, minus 4 times 1 times 200, all divided by 2a, so times 2. So we have 40 plus or minus the root of, so that's 1600, I think, minus 800, so that's just the root of 800 over 2. And so we're going to get two values here. So it'll be interesting to see what we get. I think that notation's kind of crappy there. So I meant to say QF gives us that x equals that and x equals that there. I like that better. So let's finish it off. 40 plus the root of 800 divided by 2. So x1 is, so we get 34.1 meters. Or a second value using subtraction, 40 minus root of 800. divided by 2 and 5.9 meters. So maybe think about this, guys. Both of these answers have meaning. Can you think about what their meanings are? Maybe pause the video and think about that for a second. So the Lagrangian point, the point where if we put mass 3 between these two guys and it would just float there and it wouldn't move, is 5.9 meters. If you place the object, so I'm just writing a conclusion here, M3 should be 5.9 meters from the 10 kilogram mass. If you place it between them, 5.9 meters from the 10 kilogram mass, the net force would be 0. They'd cancel each other out. But what does this 34.1 meters mean? Well, it means if you were to place kind of M3, don't need to write this down, but on my screen, like way over here, what you would find is that both F13 and F23, at that point, the gravitational force of 1 on 3 and 2 on 3 would be the same, except that they'd both be acting to the left. So the object would actually move. It would actually accelerate to the left. So that answer does have meaning, but in that case, the gravitational net force would be to the left and it would move. So there would be some net force, but in between, the net force would be 0 because these are equal and opposite. But here, they're equal and in the same direction. So I thought that's a pretty fun question to do with you guys. A little bit more involved, but I hope you guys would agree. It just requires a bit of grade 10 math. What is next for us? In our next lesson, we're going to apply Newton's laws of gravitation to what we know about uniform circular motion. We're going to discuss satellites, which is going to be pretty fun. And satellites just don't have to be like our traditional idea of like a communication satellite going around the Earth. In fact, like the moon is a satellite to the Earth, and the Earth is a satellite to the sun, and the sun is a satellite to whatever it's orbiting at the center of our galaxy. And we can apply the physics of satellites to many different things. So that's pretty cool. But that's for next time. Hope you guys are staying well. Have a great day, and we'll see you soon.